recording here. Here. Meeting, record settings, my computer, and record meeting. And here, Dropbox. Okay, can you all hear me?
Yes.
Yes, I did.
Okay, I'm gonna share my screen. I think you all are watching my screen now. Okay, let's see. So, maybe I should open. Give me 1 second, please. Here, this one. Okay, should be here. Yeah. So, I'm gonna show you the exercise that I'm gonna do. It's something really simple. It's just a cantilever beam. This one. With a point load in the free end, and then I'm gonna compare the maximum deflection at the free end with this analytical solution and with the numerical solution that we get from ABAQUS. Now there are different ways in which you can solve this problem, and the first one is you can use beam elements, or you can use 2D plane elements, the plane strain or plane stress, depending on which boundary conditions you want to consider, or you can do like the 3D model and simulate this with 3D elements. For this tutorial, I'm gonna do the 2D plane strain elements. Okay, the first thing that I'm gonna do, I'm gonna open a new, what's going on with this? I'm gonna go to research, I'm gonna create a new folder. A new folder. And in this folder, I'm gonna press in my keyboard Shift and right click, and then I'm gonna open my PowerShell in this folder. And in this PowerShell, I'm gonna type ABAQUS CAE. I open ABAQUS this way because I like to avoid setting my working directory, but I'm gonna show you how you can set your working directory if you forget to open ABAQUS this way. So I have this window. In this case, I'm gonna create a new model, so I can just close it. And here we have this window. Okay. So this is ABAQUS interface. It's an idle, and as any commercial software, it has in the top part a few deployable menus: file, model, viewport, view, part, share, features, tools, plugins, help, and so on and so forth. Um, this was developed by Dassault Systems, which means we can have a controls similar to SolidWorks. And the way to activate these SolidWorks controls are by clicking here in Tools, then you go to Options, and by default I have SolidWorks, but by default it comes with ABAQUS CAE, so you can just change it to SolidWorks. It's a step that I like to do because then I can do zoom in and zoom out using my scroll button, and panning also using my scrum button. Okay, let me just organize this a little bit. Okay, now here in the top we also have new model, open whatever file you have, save, print. Now this one, current work directory, is where you are going to store all the different files that Abacus is going to create while you are doing anything there. But you can also set the working directory by clicking here in File and then going to Set Work Directory. And this menu will come up, and then you can look for the folder in which you want to work. It has by default the installation folder, but since I open it using my uh, PowerShell, then this was, oops, I closed what I didn't have to close. Again. By opening Abacus this way, you can avoid setting your working directory, basically. Please, if you have any question, just um, raise your hand. Sorry, just speak and let me know your question. Um, so that's the working directory. Here we have a couple of predefined views of the model. You can have, these are also view manipulations. Uh, I don't think you will be needing any of this too much. This is the perspective of or perspective on. Uh, yeah, I don't think you will need to use these ones in the top too much. Now, on the left we see what I call the tree. We have parts, materials, sections, assembly, steps, all of these different controls on the tree, and we also have these different modules that we can verify on the module tree or deployable menu. Part, property, assembly, step, interaction, load, mesh, optimization, job, visualization, and sketch. Now, some of you might not be uh, familiar with finite element methods, and maybe I should just open a presentation in which I can use to explain you more or less what it does. Let me see. Sorry guys, I'm having problems with my PowerPoint. Browse. This one. So basically what we do with finite elements, we just take like a big domain, like a big part or a big component, and then we discretize that domain in these small squares or elements, and then we find the solution of differential equations in the corners of those squares or elements. This is just a traditional first order quadrilateral element, and we have 4 nodes in the corners. Sometimes you might see more nodes inside the element. It just means that it's a higher order element. And we basically find the solution of the partial differential equation in these nodes, and then we use interpolation functions to interpolate the solution inside the element. So by discretizing our domain, in this case this cross for example, into simple elements, we can solve a linear system of equations to find the solution of the partial differential equations. So this part, which is modeling a part, is very similar to SolidWorks. Here you have create part, or you can have the part manager, in which you will have create, copy, rename, delete, and so many different controls for parts. So it's the same as SolidWorks. You first create a part, and then you can do an assembly of different parts. Now let's go ahead and let's create that part. Remember that we're dealing with this problem, uh, cantilever beam, and I'm gonna create a part by clicking here in the first control. Now I can set a name. Let's call this beam. This is going to be a 2D. We can have axisymmetric problems like, for example, shells or tanks. 2D planar elements like plane stress or plane strain elements, or even shell elements. And we can have 3D parts, solid shells, wires in 3D, and so on and so forth. In this case, it's going to be a 2D planar element. It's going to be deformable. You can have rigid bodies, but in this case, we want to analyze a deformable body. And since I'm going to be drawing in a plane, you can draw either points, wires, or shells. In this case, I'm going to do a shell. Now, as you see, I haven't set any dimension or units in SolidWorks, and that's because you don't use dimensions here. You will have to follow, let me show you, ABAQUS units, this kind of table. Basically, if you are in the international system, you can use meters, newtons, kilograms, or you can use, like if you are using millimeters for lengths or for a space, then your mass is going to be in tons and your stress is going to be in megapascal. So you have to respect this table all the time, and you as engineer has to take into account these units all the time. In this case, I'm going to do 10. So here you can draw point, lines, circles, squares, and everything that you can do in a sketch in SolidWorks, you can do it here as well. So this is like learning how to model in SolidWorks 2.0. Now you can either draw with your mouse, or I'm gonna delete this, everything actually, or I can just define coordinates here in the bottom. Now, every time I click something here on the left, or whenever any action is active, you will see a message here. So in this case, it's asking me to sketch a section for the planar shell. And that's what I'm gonna do. I'm gonna define my first X coordinate and then my first Y coordinate, and then the second pair of them, and that's what I have. I have my beam, right? Here you have multiple controls. You can do curves. You can set lines as for construction. You can copy curves. Have parallel curves. You can also set constraints and relation between these lines. Coincident, concentric, equal length, equal radius, and so on and so forth. You can define dimensions using this control here. Let's use, for example, this one to define this length. And this one here. And let's suppose that I did a mistake for whatever reason. And I want to modify this dimension. You can come here in Edit Dimension Value, select the dimension you want to modify, and then you will have this menu. As you see, we can also have functions of dimensions to, if you need to draw a curve or whatever. You can undo or redo. You can delete or select or drag items. I think that's pretty much all you need in a sketch. Basically, this module is just to draw uh, the different planes of a part. So once you're finished, you can deactivate everything, and you will see that you can either click here in Done, or you can just click the scroll button on your mouse. Now remember that I have SolidWorks control in my case. So if I scroll up, I zoom out, and if I scroll down, I zoom in, and I can rotate in 3D or 2D by clicking the scroll button in my mouse. Remember that we have these default views here in the top, so I can just come back here. If I am very into in the drawing, I can just click this button, auto fit, to fit the complete view of my drawing or my part. Or if I am too far away, I can also use this to draw like a zoom in box. So that's these controllers right here. You can use this one also to pan or drag the part around. And this other one, rotate view, to do what I was showing you before. Okay. Since I'm done with this cantilever beam, I'm gonna just click here in done. And then we have this cross section. No, sorry, not the cross section. It's like what we're watching here, just a square, that black square that we have there. This will be my beam. Any questions so far? Okay. So let's continue to property. Okay, here you have more controls. You can do extrusions if you are modeling 3D bodies. You can also extrude shells. You can do extrude cuts through material. So if I want to have a hole here, I can just draw a circle there and then extrude that circle. If this were a solid body, we can have we can create coordinate systems, and we can copy and we can switch shells. If you know how to model shells in SolidWorks, you can create partitions. Sometimes these are important either to define uh, boundary conditions, or if you want to define different materials, for instance. So let's use, in this case, I'm gonna create a partition of face, and I'm gonna sketch. And basically, I'm gonna select this center point and this center point, just to show you what you can do with these partitions. And now I have two subdomains in this full beam. This also is helpful if you want to define like one type of mesh in the bottom and a different type of mesh in the top, or in different parts of your domain. And we will be checking how to do meshes in a moment. Okay, now I'm gonna, well, these are just symmetry, creating mirrors and creating fillets and rounds. I'm gonna continue, sorry, to property. And since we want to model a mechanical problem, a beam of certain material in which you're applying a load and it's fixed in one end, we have to create the mechanical properties for the beam. So the first thing that we're going to do is that we're going to create a material, and then you have this window. We can call this material 1 is fine. And then you will have here the general properties, density. You can have mechanical behaviors. The material can behave in an elastic wave, an hyperelastic wave. You can have thermal properties. You can have electric properties and other properties. In this case, I'm going to use only elasticity, elastic properties. And the material that I'm going to model is an isotropic model. Poisson's ratio, of course, 0.3. And maybe 200 megapascals. And that's it. We can click OK. So if I select the material manager here on the left, you will see that here we have a list of materials. We can again create, edit, copy, rename, even you can invent your own imaginary materials here. Then I'm gonna create a section. In this case, I'm gonna use a solid homogeneous section. You can have shell sections, beam sections. Now remember that this problem, you can do it with beam elements, and in that case you wouldn't draw a square, you will draw only a line. But then you will have to define like a cross section area for that beam. In this case I am defining plane strain, which means that the out of plane strain of this beam is going to be 0. And therefore it has stresses in the out of plane direction. So for this case, I'm gonna use homogeneous material. You can define a name for your section, and here you can assign the material. Now, if for whatever reason you forgot to create the material first, don't worry, you can just create the material here, and it will be stored. And then I can define like a thickness for my plane strain element different than 1. By default it's 1. I'm gonna leave it there. I think it's fine. Now if you remember, the height of this beam was 1 and the thickness is also 1, so it's a square cross-sectional area for this beam. So right now I just created the material and I create a section, an homogeneous section. And remember that the material was isotropic. Now I'm gonna assign that section to my beam by clicking here, and you see that immediately there is a message here: select the region to be assigned a section. These sets is how ABAQUS organizes the information. So you might have different sets for the elements that are gonna be in this top part, and a different set for the elements that are gonna be in the bottom part of the beam. Let's suppose that maybe I want to do a composed material, right? And then I can define different mechanical properties for each layer. And this is one way in which you could do that. But in my case, I just want a complete beam with the same material. Now, what happens when I only click one of the two? Only one gets red and the other one remains the same. One way to select both of them is I can just hold the left click in my mouse and create this selection box, and it will automatically select everything that is inside that selection box. Or I can just click the first one, and then pressing Ctrl in my keyboard, I can select also the second one with my mouse. Sorry, using the Shift button in your keyboard. Now, if for whatever reason I selected everything and I only wanted to select one of them, I can use the Control on your keyboard to unselect any of them. So that's how you can select multiple things at the same time. Questions so far? Good. We can move forward. I click done. You can always or either click done or just click the scroll button on your mouse, is the same. And here I have the list of sections that I have. Again, if for whatever reason you forgot to create a section before, don't worry, you can just create the section by clicking here. And then you can assign the thickness from the section that you created or from a geometry. It's the same. Now that all of my beam has section defined, it suddenly changed to green, and green here indicates that that part already has a section assigned. Since I don't have to assign any other section, I can just click done. This is to create composites layups, like one layer of, I don't know, wood in one direction, and then another layer of, I don't know, carbon in another direction. You can let's 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 leave this for a different time. This is just for composites, and I don't think you're gonna be modeling composites too often. This control here is to create profiles. Remember that the beam can be only with beam elements, and here will be where you have to create the cross section of your beam. And there you have different cross sections: box, pipe, circular beams, L profile, I profile, T profile, many of them. Again, you can do partitions here, and I think these three in the top are the most helpful controls in this module. Now, if you have multiple parts, because you are modeling an assembly of different parts, you will have the list of parts here, and you can go from one part to another one using these arrows here. Also, you can have multiple models, like with slight variations or completely different models, and you can have the list of models here. As you see, everything that I'm doing corresponds to the model number one, but then we can see how we can do more models. Next, I'm gonna go to the assembly module, and here is where you call all these different parts to create an assembly. In this case, we only have one part, which is the beam, so that's fine. But here you can do linear patterns, circular patterns. You can translate a part. Right now, I have the origin here, and then you might ask, okay, what if I want to put the origin here? You can either move the whole assembly, or you can just create a different origin here and set that one as your default for the simulation. But for this case, it really doesn't matter. You can rotate parts, and you can, when you have multiple parts, you can like add constraints between parts as you did in SolidWorks. You can do Boolean operations like merge different parts or cut interceptions of one part and the other one. This would be more helpful when you have complex part or complex assemblies. Right now, the only thing that I did is I imported this part. Now, when you import, there are two different ways to import. You can either have a dependent part or an independent part. In this case, I use dependent to have my mesh dependent on the part. Let's go ahead and change to a step. And this is a very important stage of the simulation, because here you define which kind of analysis you want to do. There are many different analyses. So you can have static analysis, in which the inertial effects are ignored. Basically, this includes different numerical methods to satisfy the governing equations throughout the simulation. You can have heat transfer problems, dynamic problems. Implicit or explicit is just the numerical method that is used to solve the problems. You can also have a buckle analysis. If you change here in procedure type from general to linear perturbation, you can do buckling analysis. If you remember your solid mechanics course, when you have a slender column under compressive forces, it buckles. It's linear until certain point, and then it stops being linear. So this buckling behavior, you can simulate it there in ABAQUS. You can do frequency analysis, like extract the natural frequency of vibration of a structure, for example. And there are many different kinds of simulations that you can do. Right now, we don't care about inertial effects, so it's not a dynamic analysis. It's just a static analysis. And you can just define a name. Also, you can do multiple steps in a simulation. So for instance, in this example that I have here, to this cross, we first apply a compressive forces, and then we do a frequency analysis. So you can do like multiple step simulations or multiple different steps in one single simulation. In this case, it's just a static general analysis. This is basically, you have for different different kind of analysis, you will have a different windows coming up. But the steps are pretty much the same, or these boxes are pretty much the same for all of them. So basically, time period here is like how long do I want this simulation to be? Remember that in a static simulation, we don't have time, so this time is actually corresponds to the numerical method being used to solve this analysis. However, in a dynamic simulation, the time is actually time, so you will need to consider the accelerations, the velocities involved in your simulation. Nonlinear geometry is for if you have large deformation simulations. So basically, when in when the element has small strains, or it's everything is linear, the boundary conditions are linear, the material behaves in a linear way. Um, you don't need to consider nonlinear effects. However, if you go to plastic, or maybe the deformation is too large, you might need to consider nonlinear effects, and the the mathematical behind the definition of the element changes. So for all of those that are considering long deformations or long displacements, sorry, strains, should consider on how on learning the nonlinear geometry effects. In this case, I'm just gonna keep it. Everything is gonna be linear. Uh, Most of the time, you will not use any automatic stabilization. This basically adds damping to the simulation in order to have a stable numerical method. As you might learn or already learn in numerical methods, some of them uh, propagate the error. So this is a way of avoiding these kind of issues. Now, in this static simulation, you can control how many increments you're gonna do, and what it means is, in my beam, I'm gonna apply a load P, but you can just like solve the system of equations involved in this problem at once by, like, you know that force is equal to stiffness times displacement. And what we solve in these simulations is the displacement and the forces in the nodes. So you can just solve the problem in one single step, or you can discretize the problem and use a Newton-Raphson to solve the problem in small increments. So instead of applying a single load P, you can just apply small increments of load and find the small increments of displacement at every nodes in the domain. So in this case, I usually use 1 million. And these are the sizes of those steps. You can just let a ABAQUS to have automatic control of this, which I usually do. Sorry. Or you can just define like a fixed step size. So all the step increments are gonna be the same. And there are considerations on doing in one way or the other. So you might want to explore and get familiar with this. And in other, well, no, you you don't really need to change anything here. Okay, right now we only have one static analysis, and as I told you before, you can create subsequent uh, steps or analysis in the same simulation. It's not the case. And then here in field output, you by default have one. So basically, this is what you want to obtain from the simulation. From this simulation, I don't really need any contact. I might want to see the forces, the displacements, the strains and the stresses, yes. at every increment. So remember that we're solving the problem in small steps, in increments. So I can define to have these solutions in every increment for the whole model, or just the last increment in a certain node, or whatever. You can have control for evenly space-time intervals if you want to create like a signal in time, or well, you have different options here. And here you can define sets and select those sets. I'm gonna show you how to create a set first. You have to come here to tools, sets, and then create. You can give whatever name you want. Now let's suppose that I'm gonna call this input, because I want to have solutions here in this point, in the neutral axis of the beam at the free end. Done. And then I might want to create another set that I'm gonna call fixed end, and that fixed end is gonna be all this line. So basically what I'm doing right now is I'm defining, okay, this line here, those nodes are not gonna move, those are gonna be fixed, and they are going to behave like the wall. I can define either a fixed nodes or pin, like if I want to this to rotate from a certain point, or even rollers if I want just to constrain one single degree of freedom. Or I can define forces as well. I can define moments as well, or stresses, or strains, or temperatures. So these sets help me to define where do I want to define something in the domain. As you saw, I have a set for this node or this point here, and that's where we are going to apply the force. And also there is where we are going to read the maximum deflection. Okay, I was showing you how to create the fields. I can edit this one. I don't need contact. I might need forces, displacements. Okay, so this is the field output, and basically we the visualizer uses the field output to show you results in the beam in this case. So I'm gonna leave that as it is. But then for the history output, which is next, is this one is the field output. Here is to create, and here is the manager, and this is the history output. And I'm gonna edit the one that is created by default. Now in this case, I don't actually need energy. I only need in one set, which is the input, this point here, and I'm gonna verify forces, not all of them, only concentrated forces, and displacements. Now the degrees of freedom in finite element methods are usually, the first three are displacements in x, y, and z, and the other three are rotations in x, y, and z. And the same for forces. Forces are usually forces in x, y, z, and moments in x, y, and z. There is also additional degrees of freedom like temperature or voltage if you have a multiphysics problem or a thermomechanical problem. So what I'm saying here is I want to request in this node horizontal and vertical displacements and horizontal and vertical forces applied to that node at every single increment of the simulation. And that's okay. And you already saw what these controls are for, so I'm gonna go to interaction. Interaction is not very used. However, when you have multiple parts or you want to define, for example, let me see, coupling or connections. Mm, let me see. Maybe you want to do a hinge in one of your simulations, for example. That's how you can define different types of connection between different assemblies, like a mechanism or yeah. Well, this is not very used, and in this case we're not gonna use it, so I'm gonna just skip it. Loads. Okay. In loads, we define what we call the boundary conditions. In this case, I'm gonna fix um, the right end of the beam. Gonna use displacement, and I can deploy the sets that I already created by clicking here in the bottom where it says sets. Instead of creating a new set that I already did, I can just select the one that I created, fixed end, and I can click here and highlight selection of viewports, and it will show me uh, which components are included in this set. Now I want to avoid a horizontal displacement, vertical displacement, and also out of plane rotation in this line here. So this will behave like the wall in our problem. And I can either define here a force or a displacement. So it's not the same to do one or the other one. If you do a force, uh, the software will control how much force are you applying. But then the unknown is going to be the displacement. And if you apply a displacement, the unknown is going to be the load. So if we apply a load, that is called load control, and if we apply a displacement, we call it displacement control. Numerically, it's more stable to use displacement control, but in this case, since we're analyzing this problem with a load, I'm gonna do the same. I'm gonna apply a load. Maybe a good exercise that you can try is you can apply the maximum displacement and try to recover the load out of that out of this equation. To create a load, you just click here, and here you have forces, moments, pressure, many different kind of loads. In this case, it's a concentrated force, and it's in this point, what is called input. Continue. And I don't want any force in X, I just want forces in Y. I'm gonna apply a kilonewton. Now you might have a signal in the forces. For example, if you have a sine wave in the force or in the displacement, you can define the, the signal in time here in creating the amplitude. And if you do so, you will have periodic amplitudes, equally spaced, even at the spectrum of the signal. There are many things that you can do here. In this case, linear ramp is fine. So what it's going to do is in time 0, the load is going to be 0. And when the time goes to 1, this is going to be the load. And it will draw a straight line between those two points. It will be like a linear increment of the load applied here. Questions so far? Wow. Either I'm a very good teacher or this is too easy. Okay, mesh. This is where we discretize this model. Um, the first thing that I will show you is this, is assigning the mesh control. But as you see, I have a dependent part model in this exercise. So instead of using the assembly here, I have to use the part, this beam. And then I can define that mesh control. I'm gonna select everything. Actually, I'm gonna select one at a time, just to show you. So in this case, I'm gonna use a, an structure mesh of quadrilateral elements. And for this one, I'm gonna use triangles, just to see the difference. And I'm gonna show you the difference. So as you see, we have here squares created, and the nodes are only in the corners of those squares, whereas in the bottom we have triangles. It's not a good practice to mix different kinds of elements, but sometimes you might need to. So this can show you how to do so. I'm gonna change these triangles for a different kind of element. I'm gonna still use quadrilaterals, but I'm gonna use free mesh. And this is what I want to show you with this free mesh. I'm gonna delete everything. Okay. I can define a, what is called seed edges, and it basically tells the software how many elements do you want in an edge or a line. So for this one and this one, I'm gonna use by number. I want 3 elements in that direction. And then I can go here in constraints and click here in do not allow the number of elements to change. That will tell the software that it's mandatory to use 3 elements equally spaced in these lines. And I can create a mesh only in that portion just to show you that. And it will create 3 elements in those edges. Now what happens if I want, for example, 3 elements in this side, and I want more elements in this side, maybe 5. And then I mesh that component. Now you see that the squares are not all the same, and we have things that doesn't even look like squares. They are just quadrilaterals. The one on the top is called an structure mesh, and the one in the bottom is called an unstructured mesh. And the difference between both of them, let me see what's happening. My computer is slow. Let's take the chances, guys, to ask questions if you have any.
Yeah, so I had a question.
Yeah,
so in what situation would you want to use a triangular mesh compared to a square mesh? Are there like particular situations where you would want to use one or the other?
Good question, Drisha. Basically, depends on the geometry. There are some advantages on using one element or the other. Triangles suffer or tend to suffer from defects on auto-locking, I guess is the name of the defect of the triangular elements. However, the mathematical formulation, I think it's easier, so it would be a faster problem to solve. Also, you can use triangles to fit better a curve or a given geometry than squares. So it really depends on the geometry. This is not.
Okay.
It's not answering. Um, yeah. Another question that might be relevant is you might have not only linear elements, you might have higher order elements. and that
Mm-hmm.
means that you have more nodes in an element, like having nodes in the midpoints of the edges of an element. So you can actually simulate curves in these elements. And those
Mm-hmm.
elements have different advantages. For example, with these linear elements, you can only interpolate a linear plane inside of the element. So you know that the linear interpolation scheme that you're using for this element is linear, and you will
Mm-hmm.
be assuming to have an error due to that interpolation. Of course, if you use a higher order, you might have more approximation, but there is problems of using higher orders. For example, if you have wave propagation problems, then there
Mm-hmm.
are spurious effects. And the thing is, by using higher order elements, you will inducing numerical errors. So you have to be careful on which kind of element you use.
Mm-hmm.
Sorry guys, this seems not to be working, so I will have to do it again. But I'm gonna just do it fast because you already saw what's going on.
Okay. Thank you for the answer.
Anytime. How many of you have used finite elements methods before?
I mean, I took a class in undergrad, and I'm taking the class right now. Um, we used um, we used ANSYS for it, but it seems pretty. Abacus seems kind of different compared to ANSYS. Like,
Yeah,
it seems more detailed.
yeah,
Yeah, Drisha and I have used, like you said, ANSYS, and then typically I have familiarity with SolidWorks as well, and I know that this is made by the same company. So I think one question I had was like, I guess, what separates Abacus from SolidWorks in terms of like finite element analysis?
good question. Well, SolidWorks is like the toy version of finite elements.
Uh,
It's just very few elements. The mathematical formulation is not very detailed. Like it has errors, and the capabilities of the softwares are huge. SolidWorks is just to teach you in undergrad, like what is a CAD, how can you use it, but like would Boeing design their airplanes in SolidWorks? I don't think so. There are more powerful CADs like Katia or other things. It's the same for finite element softwares. SolidWorks it was just to introduce you in what you can do with finite elements. But ABAQUS is what you use on research, and it's because it has been tested and it's one of the most powerful tools that we have. Okay, I reopen ABAQUS and I have this window pop up. Basically, I can recover my changes, and that's because whenever you are doing anything in ABAQUS, it will create like these Python subroutines of every button that you touch in ABAQUS is actually a line of code that is being written backgrounds in these Python codes. So if you want to like, hey, can I instead of doing all of these clicks in the CAE, can I just use Python or what we will see further the input file? Yes, you can. It's not necessary to use the the graphic interface. And actually, in research, that's what we do the most. We barely use the interface for anything, like just to create the geometry, and then we do all the analysis and modifying these Python codes and the input files. But that's for the future. Right now, I just want to recover my changes. It will take some time.
I also had another question. So,
Mhm.
in ANSYS, you could import a SolidWorks file. Can
Mhm.
you do the same in Abacus, or do you
You
have to create
you can
CAD
do
monitor?
you can do the same. You can actually click here in part, right click, and then import,
Okay.
And then there is many different things that you can import. Katia, ABAQUS input files, and you can
Okay.
export from SolidWorks the mesh as well, but there are problems on doing so. So I would rather recommend you to learn how to, if you want to model something that you want to simulate in finite elements, just
Mhm.
model it in SolidWorks. Because when you import this from, model it in ABAQUS. Because when
Mhm.
you import this from SolidWorks, trust me, there will be many errors, and fixing those errors takes more time than actually modeling this in ABAQUS. So
Okay.
just get rid of SolidWorks and learn how to use ABAQUS properly. That's my recommendation for you guys, for all of you. Okay, we were in mesh. And so this is the control to mesh the whole part, or you can hold click here. Every time that there is like this small uh, black triangle in the button, is because if you hold click there, you will see more options. In this case, we have mesh the whole part or just mesh a region of the part. You can delete all the mesh or just delete a region of the part. In this case, I'm gonna delete everything, and then I click here in yes. And what you usually will do is that you will set the same control for the entire beam. Now, having a free mesh, I'm gonna go back for a second to the buckling problem because it's what I do most research on about. You know that in the ideal world, in the perfect world, when you apply compressive forces, this will just compress. This column, for as slender as it can be, will never buckle in the ideal case. However, it buckles. Why? Because there are imperfections, either in the boundary conditions, like you're not applying the load in the perfect center of the column, for example. So there is a small moment going in the column, or imperfections due to the material. Maybe the material is not one single crystal. You have multiple crystals, and these different crystals create different stresses distribution inside the material, and that's why you have this buckling behavior. When you use a free mesh, you are inducing some, like a small version of this imperfection behavior, which can be good for your simulation or can be bad. So you have to always take that into account. Uh, However, in most of the cases, if unless you're doing a buckling analysis, it's not something to really consider. And the structure mesh would be like the ideal beam, the ideal column, the state-of-the-art column. For our analysis, that's the one that I want to use, the ideal beam. And then you can click here in Assign Element Type. Uh, I will select the entire domain because I want to assign the same element in the entire domain. And here you have a whole list of elements. You have beam sections, cohesive elements, heat transfer elements. And the thing is, for different problems, you will need different mathematical formulations. In this case, I want to use plane strain. And here's where you will define the order of the element. Either you want a linear element or a quadratic element. Remember that using a quadratic element means having more nodes and having a second order interpolation polynomial inside the element. Uh, Both has advantages, both has disadvantages. Even the quadratic might be better, but it's the system of equation becomes larger, and then it's slower to solve for the computer, especially because I am running this in my computer. Um, Explicit, this is really for dynamic problems, so don't really bother about learning this explicit. Reduce integration. I'm not sure if you learned this when you were in finite elements, but basically to to find the stiffness matrix of one element, you have to solve an integral, a double integral or area integral in the element. And to do so, we use what is called a Gauss quadrature. Basically, we only find the solution at certain positions inside the element. We multiply the solution by certain weights, and then we do a summation, and that's it. We find a numerical way of finding an integral. In other words, you don't have to actually go on and solve the integral by yourself. You just use a numerical method to do so. And when you use reduced integration, it just how is the amount of these points that you use to solve that integral. It means if I use reduced integration, my stiffness matrix is going to be less accurate, but at the same time, it's going to solve faster. In this case, since the problem is a toy problem, I don't care, so I can just ignore the reduced integration feature. There are many controls here that you will have to check when you're using one element or the other, but you can do that on your own. And remember that you can all of these different controls, you can verify it in the ABAQUS manual in internet. We see here the code of the element and then a brief description of the element. This is a 4-node bilinear plane strain quadrilateral. It's called bilinear because it's linear in both directions, x and y. Look what happens when I change from plane strain from plane stress. We see a different code here. And suddenly it activates the reduced integration again. You have to be really careful if you want to use reduced integration or not. And see that when I have the reduced integration, I have an error here or not. You can find these codes as well in the ABAQUS manual, like all the different elements that ABAQUS has. Okay, I have plane strain, linear elements, but I need to define seeds. I need to change this seed here. Instead of using 5, I'm gonna use 3. There are also some rules of thumb on how many elements do you should use in a beam like this kind of problem. I don't remember those rules, so I don't care. And also there are rules on the aspect ratio. It's not good to have like a very short edge in one element and then another edge that is super long. It will induce numerical errors as well. And then let's see what happens if I increase this seed. That looks fine. And then I'm gonna mesh everything. And then you see all these squares are my elements, and the nodes where I'm gonna solve the problem are these corners here. Remember that the size of the system of equations that you solve is the number of nodes that you have multiplied by the number of degrees of freedom that you have. One last step here in the mesh is that you should always consider to do is verifying the mesh. You click here in this green check, and then you select all the domain, click done, and highlight, and it will show you how many errors does the mesh have and how many warnings does the mesh have. In this simple exercise, of course, there are no errors and no warnings, but if you have a very complex geometry, you will start having errors. And if you have errors in your mesh, and maybe you are solving a dynamic problem, the dynamic problem will never solve, will take forever to solve. So always check your mesh before you actually use it. This is a good practice. Questions on the mesh. This is a key point on the simulation step.
Yeah, I had a question. So let's say you have a complex geometry
Hmm.
that you're trying to do some simulation on, and you use like a relatively structured mesh throughout the part,
Hmm.
but you end up getting some type of error with the meshing.
Hmm.
Like, what are some key points or some suggestions you would do if you were to kind of correct those errors or minimize those errors?
Well, regarding structure meshes, the thing is you don't have much flexibility on using a structure mesh. And a structure mesh is for a very simple geometry like the one that I'm modeling. But for example, if you have a complex domain and you want to use an unstructured mesh, my suggestions are try to add partitions, and then you can have like fit small elements in these small areas. That will help the measure a lot. Second, try to use to change the seeds in the edges of your domain. Having control on how many elements you want along a curve or along a line might help the measure a lot. And finally, if none of those work, um, then change your element. Instead of using square elements, maybe you will have to use triangles, and there's nothing else that you can do. Um, those would be my suggestions. Now, me personally, I've been there is a problem that we've been facing. Let me see if I can show you. Exactly. No, yeah. For instance, this geometry is very complex. It's shell elements. All of those are quadrilateral elements. Sometimes you might want to use this software, Gmesh. I don't know if you're familiar with this. And the good thing with Gmesh is that you can create an ABAQUS mesh in this software. Uh, the measure is more powerful than the measure in ABAQUS, uh, but using Gmesh is not trivial. You will might need to learn how to code in Gmesh. However, if you're working with Dr. Milwater, Daniel Ramirez is an expert using Gmesh, so you can just ask him.
Okay, thank you.
Yeah. Did I actually answer your question?
Yeah, no, because I've had trouble in the past where some of my meshes give me errors, and then
Yeah.
I'll go back and try to fix them, and then I end up adding more errors. So I was just wondering, like, from your experience, what do
Yeah.
you have you done in the past to fix those errors? So
Yeah.
it definitely answered my question. Thank you.
Okay. Yeah, the key things would be adding partitions and using more elements through the seeds. That that for sure would be the first thing that I will do. Okay, we're almost done. An optimization. I don't think you will be using this. This is when you want to do topology optimization, or you want to reduce material somewhere in the domain, or you want to find an objective point in a optimization problem. But this is honestly for really advanced users, so don't even bother on learning optimization yet. Finally, the job. I have everything. I have a mesh, I have boundary conditions, I have mechanical properties, I have a geometry, I have everything. Now I can submit this, and I will show you through the job manager. The first thing, I'm gonna create a job, and I'm gonna call this beam plane strain. Continue. These are the general features of your job. If you want to run it in parallel, well, you don't really need to change anything here. Just click OK. And the first thing that you might want to do in your first few simulations is to check that everything is okay. You click here in Data Check. It immediately will create an input file with the .imp extension, and, and the finite element divides in three stages: pre-processing, processing, and post-processing. What we just did is the pre-processing, and the software is just validating that file. The processing is what the computer is gonna do all these calculations on the system of equations, and then the post-processing is getting those results to create uh, plots, diagrams that will allow you to have conclusions as engineer. Okay, it says completed successfully. I want to show you the input file real quick. Now you see that I have more files in the folder that I was working on. I have the input file that is basically a list of nodes, like the geometric coordinates with a list of elements. These are the connectivity of those nodes, how those different nodes are interconnected to create elements. Check that I have here my type of element, plane strain with 4 elements, quadrilateral element. Sorry, with 4 nodes. And then we have the sets that I created. Well, these are the default domain. The section that I created, remember that I had a fixed end and an input, a point. These are the material properties, the mechanical properties, the Young's modulus and the Poisson's ratio. These are the control parameters of the static step analysis that we're doing. Here we have the fixed end boundary conditions and the load applied in the input set. This will be input, the second node. And then the outputs that I'm requesting. Node outputs and the history output and the end. So this is the input file, and you will see that everything that has 2 asterisks is a comment, and everything that has 1 asterisk is a function. And all of these functions are documented in the manual. I strongly suggest you to read and get familiar with these input files, because at the end, this is what you will be writing and rewriting more than actually using the graphic interface. Try to get familiar with all of these different functions and what are the different parameters and how to use them. In the meantime, the check was completed, no errors, so we can submit it. Once you do data check, you can click continue. If you click submit, it will check again, and I want to avoid that, so I will just click continue. And then there is a small window here that I needed to click OK. As you see, it says here the input file has been submitted for analysis. And my computer is going like crazy. Questions so far while this is computing? It says the status is running. I can check the monitor if I need. It will show me all the different iterations that the computer did to find the solution. Also, okay, this might be one of the most important things. What if my simulation didn't finish, or what if there is an error in the simulation? Where can I find the error messages that will help me to improve my model? First, always check the status file. This has the steps that it did. Sometimes, due to numerical error, it will stop at the beginning of the simulation or close to the end due to nonlinear behaviors, probably. If you see this message, then you can be happy that your simulation is done. And another source of errors is the DAT file. you can just type in find error, and if there were any error, it will just find it. By the way, this is Sublime Text. This is the editor that I use most of the time. Um, at the end, it says analysis completed with 5 warning messages in the .dat file and 1 warning message in the message file. If there were any errors, it will also tell me check in the message file for errors or something like that. And the last one is the message file. In the message file, you will see information concerning each iteration of the process. Therefore, this file is super long. But always, if there was any error at the last iteration, it will tell you what kind of error was happening. Then remember, that file, status file, and message file. Those are the best places for looking for errors. The simulation is over, it's completed, and then we can check the results. And then we have here the results of this beam with the point load at this end. Here we have the von Mises stress. If you remember any of these failure criteria, we have also Tresca, very important one, or the main stresses, the eigenvalues of the stress, the eigenvalues of the stress. Remember that I want to compare my maximum deflection here, and I can not only see stresses, I can see strains, principal strains, concentrated forces. We only have one force there, therefore that's the highest magnitude in the domain. Reaction forces here on the fixed end, magnitude and horizontal component, vertical component, or in this case displacement, maximum displacement. I want the vertical displacement at this point. Now I can use this tool. This is called the probe. Let's suppose that I want to have all the components in all my model in displacements like this, and then I can just write this big table in a text file, results.txt, and then I can increase the number of significant digits, and then I can click OK, for example. Or let's suppose that I want a screenshot of this without actually taking a screenshot. I suggest you to go to File, Print, then you click here in File. In this case, I want to save a PNG. I usually use 3000 in the width control by clicking here, and then I can rename this results1, and then I click OK, and it will be stored here without background, without any background, and then I can paste this in PowerPoint for a beautiful presentation for your boss. Or you can do animations by clicking here, animate time history, and it will show the beam being deflected. I can also control the this is going to crash again. Questions. Let's take the rebooting to ask questions, guys. I want you to talk, to participate.
Yeah, I had one question. So I'm pretty familiar with using like the ramp function, like when you were talking about creating a load, and you were talking about the function being a ramp, applies a load. But do you know of any situation where that's not applicable, or?
Yes.
Okay. Can I discuss that?
let me show you my presentation from today actually. This is the problem that I was solving actually in my code. But basically, the force that I was applying to this weird column was actually a function of time. This is what we call a Rickard pulse. And with this, we want to find and identify imperfections in a domain. Basically, this is used for structural health monitoring. As you can see here is an example of a time signal of the force. And then what I do is I just go to MATLAB, I create like a vector or an array of time and amplitude, and then I just copy that table in ABAQUS, and that's it. That's how I have my boundary condition as a function of time. It's just that I deal with, most of the time I deal with wave propagation problems. So in my case, it's an everyday thing.
Okay, thank you.
So I had another question. So you mentioned that you usually don't use the graphical interface and you're just changing numbers in the data file.
Uh-huh.
So usually whenever you're doing the changes in the data file, how do like the changes or the results, how are they saved? Like once you save the data file, how are the results updated, I guess?
Okay, good question. Once you modify the input file, let's suppose that, I don't know, maybe I want to change the boundary condition. Suddenly I don't want to apply just 1 kilonewton. Maybe I want to apply 2 kilonewtons. It's just faster to change this one to a 2 here. And then in the PowerShell, I can run ABAQUS without actually opening the the CAE, and I will show you in a moment how to do it.
Okay.
Or let's take the change now that it crashed. Uh, you will type ABAQUS and then the word job, or you can use only the letter J equal to the name of the input file. Now this input file is called BMPE. That will be exactly what I have to write here, BMPE. And by clicking enter, it will run. And it will take the same time as if I do it in the graphical interface. Now, as you may know, we also use SHAMU in UTSA, their supercomputer, and we basically access to SHAMU through this mobile extern. This is a Linux communication system. It's the same. We basically load ABAQUS in SHAMU. We send our input files there. For example, let me see if I have any here. Yeah, as you see, I have files here. And then we run ABAQUS as I am doing here, just from code. ABAQUS job equal whatever input file. Now there are additional controls that you can use in this coding way. The first one is maybe you want high precision, like double precision for your results. Of course, it will need more memory and more time to compute. Or maybe you want to use parallel, right? For instance, my computer has like I'm not sure, like 4 physical cores and 4 virtual cores. Maybe I want to use 2 cores in parallel. And since I am parallelizing the the program, it would run faster, right? Not necessarily twice as fast, because there is some communication between the cores that is necessary and that is really slow. But for instance, in SHAMU, that we can use up to, I don't know, 64 cores at the same time, 128. You might want to use more cores there. We are only restricted by how many cores are actually available or how many licenses are available.
Okay, thank you.
You're welcome. Yeah, Adrian, by running ABAQUS this way, it will automatically overwrite uh, the results files.
Mm.
And that's actually a very good question because it takes me to a second point, and it's be careful whenever you're changing things in your models. You might
Mm.
want to have the previous version. So what I do is I always, whenever I'm gonna do a modification on an input file, I save it with a different name,
Mm.
and then I have multiple results. Okay, we were in visualization. I have to, for instance, we maybe I use the graphic interface most of the time just to visualize the results. And as you see here, the results are the file with the ODB. Now, if you want to actually open that file in a text editor, uh, you won't understand anything of that because it's really weird. So you need ABAQUS to interpret those results.
Mm.
However, there are ways in which you can, from the input file, store the results uh, in a different way, maybe in a text file or any other way. I just don't remember how. Okay, we were here. I was doing the animation, and I want to change the velocity of the animation. For instance, I don't want to run that fast. I can just do it from here by clicking here in these animation options. Other thing is I can just control here which moment in time do I want. And as you see, the time here and the increment changes. This simulation took only 57 steps to solve from second 0 to second 1. You can have multiple viewports. I can click here and create viewport and then organize them like this probably.
Mm.
And then I can display here the principal stress, and here I want to display the principal strain, for example. You see? And then I can do animation of the two of them at the same time. I don't know why it's not working. Yeah, my graphic board is done, man.
So this one is a square cross section, right?
No, well, yes, sorry. And that's because the height that I used was 1 and the thickness was also 1.
So can you also see like what's happening on the cross sections?
In this case, no, because I'm using plain elements.
Yeah. Okay.
To do so, I will need 3D elements.
Mm.
But using 3D elements means more nodes and more degrees of freedom, and then the system is bigger, and then the
Mm.
computer takes more time to solve.
But basically, that's something, yeah, that you would have to predetermine, like
Yes,
input it before. Okay.
yes, after of doing the simulation.
Mm.
Sorry, after not, before doing the simulation.
Yeah. Yeah. Okay. Got it.
Something else. Okay, if you click here in common options, you can hide the mesh, for instance, free edges. This is just visualization controls. You can change this map of colors. This is called jet, but you might want a different color map for whatever reason. Now remember that I did a history output. I can right click here in XY data, create, and then I will have this window come up. In this case, I want to see the history output that I requested, and these are the options that I have. Remember that I was asking for the input set, and I requested the forces and the displacement. Now let's see the force displacement curve. It's very obvious, and ABAQUS by default will show you the time in the x-axis and everything else in the y-axis. There is a way around in which you can change the x-axis, but I don't know how. What I usually do is I create these plots here, and then I click here in report, X, Y. I have this list of things that I have plotted, and then I change for, I don't know, force versus displacement, txt. I don't want to append anything, the highest precision possible, and then OK. And then if I go, I missed a T at the end, txt. Okay. And then if I open that file, you will see that I have the time in the first column, and I don't know if this is force and displacement. Let's see the last one. So this one is force and this one is displacement. Then I can read this in I don't know, MATLAB, Python, whatever you want, and create beautiful plots. And that's what will be the post-processing part of your analysis. I think that pretty much covers it all. Something that I forgot, and is very important, guys. As you saw, this crashed several times during this session. The first thing that I should have done was save this. And then you can save the CAE, beam, CAE. And this will save like the ABAQUS section, everything we did so far. So next time I don't have to do all of this again. I can just open that CAE file, and it will have everything updated. It's not the same as the input file. The input file is what actually ABAQUS reads to do the simulation. But since you're learning, it's always good to have the CAE file, just if you have to do something from the graphic interface. What else am I missing? Let me go back. Okay. One final thing, and that's it. As I told you, you can have multiple models. Let's maybe copy this model, and I'm gonna call this maybe plane stress, right? And then we can compare what is the difference if I use plane stress or plane strain. Remember that I click in S4R here in assign element type. I select the domain, click done, and then I change the element from plane strain to plane stress. Okay, done, and then we create a different job. I create a different job. This one is gonna be beam plane stress. And make sure to use the model that you want to simulate. Okay, and then submit. Now, as you see in this CAE section, in this K section, I have two different models. And you can have absolutely different things from one model to the other one, or they can be as similar as you want. Now, who of you can plug this in your calculator and get the analytical maximum deflection?
I get that.
Okay, thank you.
The force was 1,000 newtons, right?
That's correct.
And the length was how long was the beam?
10.
10.
Yeah.
Over 3, I believe E was 200 times 10 to the 6.
Correct. Again.
I is for
It's 1/12.
Okay.
Because the base was 1 and the height was 1 as well.
Okay, so it's 1/12. Good. So let me run this.
In the meantime, I'm gonna create the second result. Now you see that there is like a slight variation between the force and the displacement.
The answer I got is like 0.30 and 2. So 0.0002.
I guess I got the same. Okay. Yeah, look at this. Pretty much the same.
Yeah.
And then let's verify. Results, plane stress. Look, this is the maximum deflection for
Yeah.
plane stress, and this was the maximum deflection for plane strain. Pretty close one from the other one. But as you see, there are differences using one element or the other one. I would like to challenge you. Well, Vittorio has to do it, but the rest of you don't. But I would like to challenge you to do this same exercise using 2D beam elements, and then try to do the same exercise using 3D elements, three-dimensional elements, and compare. And then you can conclude which kind of element was most or the best fitted for this kind of exercise. And then since most of you already know how to code, then you can plug this equation in MATLAB, and then you can have like the deflection as a function of x of the neutral axis of your beam, and compare with the results from ABAQUS. That would be a really good starting point. Okay, guys, I think that covers it all. I expect that you have learned something new today and enjoyed this introduction.
Yeah, thank you. It was helpful. Thank you for your time.
Yeah, my pleasure.
Yeah, thank you so much. I learned a lot.
Okay, guys, I'm gonna stop the recording. I'm gonna share the recording with you guys.